Alright, so let's begin the session. So in the morning we have seen the different vein shapes, backward curved veins, radial veins and forward curved veins. Okay, so we have seen the velocity triangle for all those things. Now before starting, let's see this question. Okay, so let's read this question. In the veinless space between the impeller and the diffuser vein in a centrifugal compressor, the angular momentum varies in the following manner in the radial direction. So you have the four options given, right? So tell me which is the correct one. The question is, in a veinless space between an impeller and the diffuser vein, okay, in a centrifugal compressor. Okay, now the angular moment, how it changes, whether it increases, whether it remains constant, whether it remains decreases, or first increase and then decrease. Already we have covered this particular topic.
I guess remains constant.
Okay, any other answer? Anyone? Your voice is not at all audible to me.
Remains constant, ma'am.
Yes, absolutely right. So as I've said over there, the angular momentum will remains constant. Okay, this is the right option. So this one they have asked in 2017 question they have asked. So each and minute things are very important. Okay, so have a wide clarity with the concept. Okay, so now we will see this the performance or comparison between of the backward curved blades, radial and the forward curved impeller blades. Okay, so before moving that, one thing, let's look into the figure 8.15. You can see over here 8.15. Okay, it's a ratio between, it's a effect of impeller blade shapes on performance. Now how we judge the performance of the compressor, it's how it is moving with the amount of mass flow rate with an pressure ratio. Now sometimes the pressure ratio can also be noted in terms of pressure head. Okay, so they may not always ask you the pressure ratio. They can also use a term called head, pressure head, or only head, H. Okay, they can also use the call as capital H. Now
Screen is not visible, ma'am.
Excuse me.
yes,
The screen is not visible, ma'am.
screen is not
Yeah.
visible. Okay,
Yes,
Ma'am, we
ma'am.
are lost.
okay, let give me a second. Okay.
Okay, ma'am.
Yeah.
Right. So we will see the performance criteria of this backward curve plate, radial curve plate and the forward curve. Okay. So we will see how this things are vary with each other. Now first we will see the effect of impeller blade, how it affects with respect to the performance. Now when we talk performance in an centrifugal compressor, we will see the relation between the mass flow rate with the pressure ratio or the head. Now first look for the backward one, okay, backward curved blade. So in the backward curved blade, if I want to draw, how it will be like this way. So you have to remember the pattern of the blade. Okay, now in this backward, what we can see that as we increase in mass flow rate is increasing. What is happening with the pressure ratios? Pressure ratio is decreasing with the pressure ratio. Okay, now let's move to the forward one. Let's make it B. Forward one, what is, how it looks like? It will be like this. Okay, now in the forward one, as we increase in mass flow rate, there is an increase of pressure ratio. So we know, right, what we know, where our where the pressure ratio is more, right, so our efficiency will also be better. Where the pressure ratio is more, then the efficiency of the particular component will be also be enhanced. Now look to the radial. As we increase in mass flow rate, the pressure ratio remains constant. Okay, now then what is a change or difference in the backward curved blade and the forward curved blade? So it is very clear that it will be slightly better. In the backward curved blade, it will be slightly better in efficiency, and the most important thing, it is more stable as compared with the other one. This one will be more stable compared with the other radial at the forward curve. Okay. And among this, which one will have we can produce highest pressure ratios? It can produce a highest pressure ratio is a forward curve blade among the all, but it is less stable. As it can produce a high pressure ratio, it cannot perform a stable flow. Okay, stable flow over the particular blade. Okay, this is another point. Okay. So let's see, its efficiencies are lower than that are possible with a backward curve or the radial curve. Okay, so it will be efficiencies are lower that what we expected in compare with the backward and the radial curve. Okay, this is an important one. And if I want to look for the best performance point of view, so we will be using for the radial one. If we are looking for the best performance wise, we will be looking for the radial one because it is a moderate one. Okay, neither it is more stable, neither it is less stable, it is ranging between that. And next is, as increase in mass flow rate, pressure ratio remains at the same point. There is no variation. So it is also in that point of view also it is in the moderate one. Next we will now we will see in detail performance for the impeller and diffuser and also for the inlet casing. So already we have discussed this part, the elements of centrifugal compressors. So here first we have the inlet casing. Followed with the impeller, diffuser and the volute. Okay. Now just give me a second.
Ma'am,
Yes,
I have a doubt, ma'am.
yes please.
Ma'am, in morning you told in impeller and you said like it will be working like 50%. In impeller 50% of the pressure will be rising and in diffuser 50% of pressure will be rising.
Mm-hmm.
Ma'am. Then how do you say pressure ratio will?
No. Okay,
I
that's a
got
good.
little confused.
Yes. Okay. So, okay, let me take it over here. Okay. So, you remember there was one graph which I have shown. Okay, the P versus the channel length. This is a channel length. Okay, and we had 3 locations. One was like this, and remaining was going like that. You remember this graph? 0
Yes,
to
ma'am.
1, 2.
In inlet casing, it will be reducing, and from the impeller
Yes,
and diffuser.
yeah, yeah. Here we have 50%, it is increasing. Here it is 50% increasing. But here, when I was talking about only about this particular impeller, this is in case of impeller alone. Okay, so looking into that, so 1 to 2, what is happening in the point 1 to 2? Again, my pressure is also increasing, right? Pressure is increasing, but not completely. Again, from 2 to 3 point, again it will be increasing. So total, if I want to find the pressure ratio over here, then P03 by P01 will be my pressure ratio then, if I need to find the each and every point. Okay, that is inlet of the impeller. This is a impeller tip. From impeller tip, it is moving to the end throughout the channel of diffuser, right? It is moving out to the volute, right? So from entering from this way to this point, right? So that will be our pressure rise. Okay, but here what we have discussed, it is only for the impeller alone. So what will be the difference? Okay, with a change in mass flow rate. With a change in mass flow rate, do not confuse with only with an the parameter. It is with the mass flow rate or in terms of discharge. That is only how the blades will be varying. The pressure difference will be varying with respect to discharge. Okay.
So ma'am, in this graph, pressure
ma'am.
ratio is for just impeller, no?
Sorry.
Ma'am, this graph is for pressure ratio of impeller.
Yes, pressure ratios of an impeller. Exactly. Not the overall one. Okay, this is only we are considering for the impeller alone. Because otherwise, if I have to, as I've said, okay, you might have a question. Here I've said where the efficiencies are lower. Here, this one is having better pressure ratio. So, pressure ratio for the what? Forward curve. I'm not talking about the overall one. I'm not talking about overall one. Okay, I'm not discussing here about overall. Here I'm only discussing only about the impeller alone, because overall efficiency high will give you the overall the efficiency will be high. If the pressure ratio is high, the efficiency will be high. But since the backward it is less, it doesn't mean the overall efficiency will be low. Okay, but see that statement, that's why they have given, though this is a scenario, but when they compile all together, slightly better in efficiency. Which one is more efficient? The backward curve is more efficient as compared with the forward one, though it is producing high pressure ratio, and this pressure ratio is only, as I've talking about, this range, that is, sorry, pressure ratio for an P02 by P01. Okay, we are talking about this, not the total pressure ratio across the compressor. Could you able to get it, this point? Please let me know.
Yes, ma'am.
Okay, right. Okay, then we have yes. Now these are the certain formulas that you need to know. Okay, now inlet casing is, as I've said, that when the flow is entering over here, so it will be like converging type. Now what is benefit of the converging which enhance the velocity, and the pressure will be decreases. Now these are two types. One is with and without inlet vanes. Okay, either they can have the inlet vanes and without the inlet vanes. Now there will be again a velocity triangle diagram if there is a inlet vane, and if there is not a inlet vane, what are the criterias. Okay, and the main function of this inlet casing, okay, as I've already discussed, is to accelerate the flow, and also when they design this inlet casing, they have to keep that in mind that there should be some minimum losses. Okay, losses should be lower. Okay, that is a main criteria, and in this particular inlet casing there won't be energy transfer. Energy transfer will begin from the impeller eye. There is no energy transfer, because some of the question they came in some years that they asked some of the options. So is there any energy a transfer in the inlet casing or not? So there is no energy transfer. Please note down this point. No energy transfer in this inlet casing, and that's why the stagnation enthalpy will also remain constant. So here in this inlet casing, mathematically we can say that the stagnation enthalpy will remain constant. Clear? Now they might give you some of the parameters. They might give the inlet pressure and inlet temperature. Then from that you can find out the density. Okay, density of that flow. Now using the density, what is our main point? You can able to find out the mass flow rate. Okay, you can able to find out the mass flow rate when it is entering inside the inlet casing. Now how to find out? This is a formula. Now dt1 means what? It is just shown in the figure. dt1 is at the tip, and dh means at the hub. Okay, the impeller, this is the impeller tip, and this is the impeller hub, right? And the CA already we have discussed is an axial component. Okay, axial component. Okay, and rho is a density, because our formula is, what is m dot? Rho a v. Okay, to find out the a, what is a then? Is pi by 4 dt square 1 minus dh square. Okay, and we need to consider the axial component, where in this case they assume that axial component is equivalent to the absolute velocity. Okay, now we will see these conditions also. Now let's come to this inlet guided vanes. Okay, inlet with and without inlet guided vanes. Just a second. Okay, so again you have to remember in this question, sorry, it's scribbling by itself. Okay, am I audible? Just let me know.
Yes, ma'am.
Yes, ma'am. Yeah.
Okay. Fine. So if the question like if they have not mentioned anything about inlet guided vanes, that means the question means when it is entering inside the impeller, so there won't be any if they have not mentioned anything, that means there is no inlet guide vanes. Okay, now what happens if there is no inlet guide vanes? So as I've said, when the velocity entered into tip, it is in the relative velocity, leaves out from the blade, then it is an absolute velocity, right? When it enters, it is a relative. This is a relative velocity. Now before starting again, we will see the basic sketch which we have seen before. Now this one was C1. Now we are looking for entering section, so we will see for the section 1, inlet 1. This is a relative velocity 1. Here we will have the axial velocity R1, CR1. Then this will be WC, sorry, not 2, will be 1. Okay, only this much we will have. Then here to here we will have our U1, right? Now in this condition, please note down very carefully, when it is without inlet guided vanes, when it is without inlet guided vanes, what happens? Okay, CT1, or we can say the tangential, what is CT1? Tangential velocity or the real velocity is equal to 0. There won't be any real velocity if there is no inlet guide vanes. Okay, if this, now consider this, now this value has to be 0, right? This value is not there. That means this C1 will overlap over here, will start to overlap over here, right? So what it will be, if it overlaps over here, then W1, then CR1 will equals to C1. The absolute velocity will be equal to the radial or axial velocity. Then this will be the U1. This will be our beta, right? Beta 1. On that case, what will happen to our alpha? Alpha 1 will becomes to 90 degree. Can I say? In this condition, when it is without inlet guided vane, just remember one thing, that is, there is no tangential velocity. Now you know, if there is no tangential velocity, you know this basic configuration of the velocity triangle. You just remember the single velocity triangle. Now if this CT1 is 0, now this will all coincide over here, this line will join up over here. Now we will get this kind of curve. Please try to draw along with me, then you will have the better clarity. Okay, now this is a triangle is forming. So what are the conclusions I can bring? In this inlet guided vanes, the tangential velocity is 0, the alpha 1, okay, alpha 1, the absolute air angle, okay, when it is entering, it is 90 degree. Okay, second, this is the second one. The third one, what we can bring is that CR1, that is radial or axial velocity, is equivalent to your absolute velocity. Alright, now from this, based on the requirement, what are the needed to find out the unknown parameters, we can find. How we can find? Here you see the expression already has been given, tan beta 1. Okay, tan means height by base, right? So height, if they are considering C1 by U1, it can be also equals to CA1 by U1, because C1 is equal to CA1 or CR1. Both are same. Both are known as the axial and the radial one. Clear? This is clear?
Yes, ma'am, clear.
Alright, because in the question, if they are not mentioning anything about inlet guide vanes, then you have to consider this strategy. Okay, next comes with
Hello?
yes.
Ma'am, could you please tell me what is the relative velocity? It is related to what?
Sorry, I didn't get your question.
Ma'am, that relative velocity, this velocity is related to what?
Relative velocity related to?
Ma'am, relative velocity, ma'am, what does this mean?
See, I'm not getting your question properly, but what I'm understanding, relative velocity is denoted by W, okay, or it is also
Ma'am,
can be.
this velocity is relative to what? When it's relative, no? So relative to what?
See, relative velocity uh, when the flow, okay, the relative velocity is only hitting the leading edge of the impeller blade, okay. Relative velocity is the only velocity which is hitting, and based on this relative velocity other velocity components are formed, okay. That axial velocity, tangential, radial, all other velocities are forming, right? Clear? So when it is entering into the leading edge of the blade, okay, relative velocity is entering, and when it's leaving out from the impeller tip, it will be absolute it will be the absolute velocity. Did you get it?
Yes, ma'am.
Okay, all right. Now we have the with inlet guide vanes. Now in the question, if they have mentioned that if there is any sort of inlet guide vanes, then what will be uh, the, the velocity diagram, okay. So unlike unlike the without inlet guide vanes, where we have seen the alpha 1 became 90-degree, right, and beta 1 was less than 90-degree. Let's go back and see. Can I say beta 1 is less than 90-degree, right? But here it's just a reverse one of the previous, okay. It's just a reverse pattern of the previous one. So here what will be the 90-degree? Beta 1, in case of inlet guide vanes, the beta 1 will be equivalent to 90-degree, okay. Now again, just remember this simple fundamental things, and from this basic concept you can find out the other patterns, okay. You can find out other patterns. Just give me a second. What you can find now, this is the horizontal line. Please draw along with me, so it will be like a memorize for you, okay. Here I am writing C W C R or C A, you can write. This is the complete U, okay. This one will be your CT, right? This will be your CT. Now what I have said, this is the beta 1 and this is the alpha 1, right? Now here what I've said, if I'm using inlet guide vanes, what happened? The beta 1 okay, will be 90-degree. That means this one has to be like this, as we have seen in the radial when it is beta 2 conditions, right? So same phenomena will be applied over here. If I need this one as 90-degree, then this one has to join up over here. That means again, always I know this one is always 90-degree. This one is always perpendicular with an impeller velocity, okay. Either it's a tip or it's a leading edge, okay. So what I will get? So this is 90-degree, that is our beta 1 is 90-degree. Now if beta becomes 90, that means this is a relative velocity. Relative velocity will becomes equal to radial or axial velocity, okay. And on that case, CT will also becomes equivalent to your Ct will also become what? It will be equivalent to the impeller velocity and c. Okay, this is the alpha. Clear? Are you getting the same pattern? Now please let me know if you have any questions over here. If you have any questions over here. Did you understood this two different concept, with and without?
Understood, ma'am.
Understood. Okay. Now okay, these are the significance from this. Okay, now sometimes in the question what they do is they ask in a very tricky way. Okay, now remember this tricky part, one thing. So okay, next is sometimes in the question if they ask you to that if they say the inlet tangential velocity is equals to the blade impeller velocity, okay, then you have to understand in that scenario they won't give you the direct thing that it is an inlet guide vanes. So if they are giving this condition, that means you have to judge it is an inlet guide vanes, or they might give you this expression. That is a relative velocity is equals to the radial velocity or axial velocity. So that means you have to understand it is the question that they are trying to obtain the inlet guide vanes. Okay, next let's move to the previous one. If you see here, this is the condition they will give that axial compressor the axial or the radial velocity is equal to the absolute one. Okay, so if this is the case, if they are given or stated this one, that means it is an without inlet guide vanes. Okay, this is another significant way that to predict that whether the inlet guide vanes are present or not present. Is that clear? Just let me know.
Yes, ma'am.
All right. Yes.
One doubt. You told that without inlet guide vanes or tangential velocities. Is there any reason?
Is that because I will tell you the reason. Okay, very soon there will be one concept called pre-wheel concept. Okay, so in that case I will tell you how why it is not 0 and why it is 0. Okay, we will see that concept. Okay, why it is not. Okay, good question. Just remember this thing, pre-wheel. Okay, so this is the reason. So we will see what it is. Okay. All right, now moving to the next. Okay, moving to that how this parameters are affecting in a design point of view. Now they ask various 1 or 2 marks questions from this kind of conceptual question. Even in the design point of view also this topic is very very important. Now yes, now as you know, this inducer play a very prominent role. Okay, this inducer only will help you to enhance the efficiency, because the better the design of the hub and the tip inducer, so better will be the efficiency or the performance. Now in this I hub diameter, okay, I hub diameter of the inducer can be determined by the number of design considerations. Okay, now first of all, that means first thing what you can do, it can induce the stress and the vibration. Okay, it induces the stress and vibration. Second, using a better manufacturing technique, it helps to enhance a smooth flow in the okay, so better the smooth flow, less the frictional loss. Can you follow it? So how to enrich that compressor efficiency? By number of what are the design consideration. The first one is it helps to reduce the vibration. Okay, now how we can leads to decrease the vibration? first thing is the stalling. Okay, we don't want any kind of reverse flow. We don't want any kind of reverse flow, and this reverse flow, it increases the pressure gradient. It increases the pressure gradient, and that will leads to vibration. Can you follow the connectivity? Right? If the turbulency, if there is not a smooth flow is not there, then definitely it will leads to an turbulency, and due to this turbulency it will leads to an adverse pressure gradient. Okay, adverse pressure gradient, and which will leads to vibration. Okay, vibration, because it will form a vortices. The vortices will lead to an vibration, and so on. So we need to decrease all those parameters. Now decreasing we can do, we either you can implement good manufacturing techniques, and also another point is to optimize the number of blades. So this is another way to optimize a number of blades. And of course, when we talk about the blades, it will depends again what kind of blades, and again there will be some connections with that. Okay. Next is a tip of an inducer eye is an important where the highest inlet relative Mach number occurs. This is another important thing when we are coming to the point of a tip of an inducer eye. Now what is that is a highest inlet Mach number occurs. Like we have when it is leaving from the, okay, when it is leaving, okay, it having a swelling motions and leaving from the tip. It is leaving from the tip. We have to be very carefully designed that to decrease our relative Mach number. Now why we need to decrease the Mach number? Again the same thing. So we will see again a kind of concept over here, right? If the Mach number is suppose less than 1, okay, maybe let's consider Mach number is 0.65. Now flow is moving, right? Now I'm increasing the Mach number of this particular blade 0.7. So what will happen gradually, at some point the Mach number will become a sonic. At some point over the surface of the blade will form a sonic, and gradually it will enlarge and it will cause a shock waves. So if there is forming a shock waves over the blade, then definitely shock wave means a pressure gradient is occurring over the blade. Now definitely it will leads to the damage of this blade, right? If the blades get damaged, the flow, it cannot be compressed as it is required. So again we need to design it very carefully. So while designing, they have to design such a way that when they will test it, the Mach number you can see in this graph, right? So what it happens, the effect of eye tip diameter, as at point diameter increases, okay, the Mach number of the eye tip also decreases. At some point again, by increase in diameter, increase in eye tip diameter, again there is a increase in Mach number. So we have to take, while designing, the minimum value where we have the least Mach number. So what the researcher do is they take various kind of models of blade models, different kind of cross section, changing the thickness and so on. They check this pattern. So they check by increasing the diameter of the eye tip with the increase in Mach number on that relative Mach number over the blade. Okay, so where we have the least value, that will be considered for a design criteria. If we increase the speed, then it will leads to an shock wave. Then obviously the efficiency, in general I can say, the efficiency of the overall compressor will decrease. Now please let me know, could you able to follow, because this is a very very important part. Could you able to follow, all of you?
Yes, ma'am.
All right. Okay. Now we will see some of the very important highlights. Okay. So we will see again this formulas will be helpful for finding for doing the calculations. Okay, so note down this formula for an unit mass of air, okay, with a torque. Okay, theoretically it can be written as Cw2 into R, W2 into R2. R2 is a tip, okay, impeller tip. Okay. Next we have the angular velocity. Okay, if the omega is angular velocity, then the work done can be written theoretically as this. Okay, can be written as this. Okay, or it can be also written as this. Please note down this formula. This is a very important formula. That is, what is Cw2 is an tangential velocity, or we can also rewrite this equation as W work done of the compressor as Ct2 U2 minus Ct1 into U1. Okay, please note down the formula. It will be helpful while calculating or solving the problems. Okay, then if I want to introduce the slip factor, okay, slip factor already we have discussed, so we can rewrite the equation of the work done by psi into U2. U2, what is U2? That is at the exit condition. Okay, impeller tip speed. All right. Okay, then another important term is an power input factor. Okay, another important is a power input factor. I think there is some please there is some error. It should be mu. Okay, it should be mu. Slip factor we denoted by mu. Okay, so it is a mu U2. Okay, please note down, it is a mu U2. Next we have, this is the if we want to include the power factors, okay, power input factors, so it can be denoted by psi. This is psi into mu into U2. Can you follow, all of you? Please let me know. So in the question, if they are giving you, yes please.
One doubt.
Sorry,
Can you go to the previous slide?
previous. Okay, just give me a second. Yeah,
Here in that WC is work done by what?
WC, which one?
WC is equal to CW.
Cw2 into U2 minus Cw1 into U1.
This will be like no slip condition.
Yes, no. This is in general. We will see in the no slip conditions. What is mean by no slip condition? Okay.
CW.
Okay. Yes, in no slip condition, what happens? Cw2 is equals to U2. So if I want to apply over here on the same time, if this is a condition Cw2 equals to U2, that means the beta 2 equals to 90 degree. If I see that graph, it will become beta 2 equals to 90 degree. Okay, so in the 90 degree, what happens? In that condition, if W1 and CW1 and CW1 and U1 is ignored, okay, if it is ignored, if in case it is ignored, then we can write as U square. Okay, can I write like this? It will become WC equals to U square, or I can also rewrite like this, WC equals to CW2 square. This is only the no slip condition. This is a general equation. Okay, this is a general equation. Now again, the slip factor, when is included, again in that, if the slip factor is considered, what we do is we just implement slip factor is mu into U2. Now another factor is added on, that is a power input factor. If the power input factor is added, okay, so we will have again the psi into mu dot M2 U2. And finally, you have to remember this thing, this power input factor lies between this 1.035 to 1.04. Suppose in case the power input factor is not given, so you can directly consider the power input factor is 1. If in case it's not given, then you have to consider the power input factor is 1. Okay. Then next, note down this formula. This is another important formula. Okay, so what is psi? That is power input factor, that is Cp T naught. Here T naught 3 means the 3 point defines the diffuser point. Okay, 1 is a impeller 1. Okay, the diffuser, exit, and the impeller intake. Clear? Or if you have a confusion with that, you can directly write down T02 minus T01 itself. No problem, either of the things are alright. Okay, mu U. Okay, it is square. Okay, there is some square. Please note down the formula carefully. While putting in the PPT, there was some misalignment happened. Okay, please write down the formula carefully.
Next to the power input.
Yes. Previous one also will be having power square terms will be there. Square terms will be here. Okay, square terms will be here. Please note down the formula carefully. I have just okay.
And here also mu only, and next to U square.
Yes, this is also mu. Okay, please note down the formula. Shall I move to the next?
Yes, ma'am.
Okay, then you have to remember this formula, how it has been arrived. Okay, so in short, you can also rewrite this equation, that is P03 again means a pressure ratio. P03 by P01 is a complete pressure ratio. Okay, can be written as 1 plus eta c psi into nu u square by Cp T naught 1 gamma by gamma minus 1. So please note down the formulas, because this formula will help you to solve the problem. Shall I move to the next? Just let me know.
Just 1 second, ma'am.
Okay. Just let me know once you're done.
Excuse me, ma'am.
Yes, please.
I'm sorry for the interruption in the meanwhile, ma'am.
Yeah.
Actually, I'm really sorry, ma'am. I need to leave the meeting right now because I'm having some sort of work, some personal issues there, ma'am. Sorry.
Okay, okay, no problem. Please, no problem.
I will just see the video, ma'am.
Okay, okay, all right, all right.
And moreover, ma'am, only one suggestion: will the PDF be uploaded, or we have to go through the PPT?
No,
ma'am?
see, I have already uploaded the PDF. As you have said that it will be much beneficial. So I think the previous class I've taken for the propulsion I have not uploaded yet, but this time I will be uploading the PDF also.
Sure,
The
ma'am.
video will be
Thank you
there.
very much.
Yeah.
Sure, ma'am. Thank
yeah,
you, ma'am.
yeah,
Thank you.
yeah. Take care.
Bye, ma'am.
Just let me know. Shall I move to the next?
Yes, ma'am.
Okay, fine. So this is another couple of formulas. So it shows the work done. This is actual formula of the work done, which we have seen over there. Okay. Psi, this is an power coefficient factor. This is a slip factor, u2 power 2. Okay. And further it can be written like this: change in temperature into Cp plus 2 psi by mu into u2 square, which already we have seen this formula. Okay. Now another formula based on pressure coefficient. Okay. Now this is the formula for the pressure coefficient, denoted by psi suffix p. Okay, psi suffix p. Okay, this is a formula. Please note down this formula. What is RC? RC is the overall pressure ratio. Okay, overall. If they are giving the P03 and P01, will be okay. The main concept is at the exit of the diffuser and the inlet of the impeller. Right? This is a main thing.
What is this IP pressure coefficient?
This is of psi. This is not y. This is psi suffix p is a pressure coefficient. It's a pressure coefficient. Okay. Psi alone was the power input factor. Okay, that was a power input factor. Psi suffix p is an pressure coefficient. Done? Done with the formulas? Can I move to next?
2 seconds, ma'am.
Okay.
Ma'am, why they are taking the pressure coefficient as W adiabatic that
Why the pressure coefficient is taking as
W adiabatic divided by W central?
because if you see the question, see this formula. Okay, this is actually why they are taking, that is very uh, difficult to say that why they are taking. It's just to identify the change in actual within isentropic relations. Okay, now adiabatic means always we know the actual one, and ideal always it is goes to the maximum limit, right? So what are the changes in this ideal within ideal to what I can say, ideal with an actual one, with a pressure ratio in terms of pressure, right? Okay, so it is a slight difference with an efficiency, because efficiency when we are taking, we are considering both for the ideal case and for an the adiabatic case it is same we are considering, right? Because when we are writing out this formula, that is P02 by P01, we are writing T02 prime by T01. We are not using prime over here, or we are not using the prime means isentropic, and without prime means adiabatic conditions. But here we are not considering it, right? We are considering both P02 prime is equals to P02. This is the assumptions we are taking in case of efficiency. But here in the pressure coefficient, both are tends to be different, and obviously the pressure coefficient at the exit in the ideal case will be much higher as compared with the actual one, because there actual one there will be some losses. We will be considering some amount of losses, consideration of some losses. Okay, that's how it has evolved with the pressure coefficient. Okay, clear?
Okay, ma'am. The W is nothing but work done, ma'am.
Yeah, it's nothing but it's a work done. Yeah.
Okay, ma'am.
So overall the efficiency can be written like this. This is the overall efficiency of the compressor, already we have studied in the gas turbine, right? So already I've said eta equals to I by A. I means the isentropic change in enthalpy with an ideal change in enthalpy. So using that relation, already we have seen this thing, derivations. So this is another final expression. Okay, so these are the final overall expressions. Now this is our expressions in terms of, this is an efficiency expression in terms of see the pressure coefficient, the your power input factor, and the slip factor. So again they might ask you a question like find out the suitable possible expressions. Okay, or they can give you the factors, they can either give you these factors, okay, the value of this pressure coefficient, they can give you the value of the power input factor, and they can give you the slip factor. Now using this you have to find out the efficiency. Now this can be also be a question. Okay, or maybe they have given all those factors, will ask you they will additionally give you the change in temperature and other factors and ask you to find the opponent factors also. So vice versa, you have to apply the concept to find out it. Okay, so always remember these expressions. Anyways, somehow they can ask and they can twist and ask you the question. Okay, so get ready with every kind of possible kind of questions. Alright, now we will start solving some of the important problems. Now first question, a centrifugal compressor under the test given the following data. Speed has been given, revolution per minute. Then inlet total head temperature is 21 degrees Celsius. Outlet and inlet total head pressure has been given 4 bar and 1 bar. Then inlet impeller diameter has been given. Then if the slip factor is 0.92, what is the compressor efficiency? Okay, so slip factor is mu, impeller diameter is d, then I can say the pressure ratio is 4. Then total pressure at inlet, that is T01, let me consider. So 21 plus 273 will become 4 2. Okay, this much Kelvin. Now speed is given. Now we can use, this is in revolution per minute, that means RPM, right? So from here we can find out U, that is impeller speed. How we can find pi d n by 60? So using this formula, pi into diameter is given, that is 75, that means 0.75 meter, into 11500 divided by 60, you will get your, okay. Now what is our main motto is to find out the compressor efficiency, eta C. What is eta C? Just now we have seen here the power factor is not given, so we have to consider as power input factor as 1. So we know that efficiency means to formula. One is that by RC gamma minus 1 by gamma minus 1 by T01 minus T02 minus T01. Okay, this is one formula. Now is there any other formula? Can we use any other formula? Here we have a slip factor. So how to utilize this slip factor? Any idea how we can proceed it?
Ma'am, we should find pressure coefficient and then put it in the formula.
Pressure coefficient is not given. Pressure coefficient is
Power input factor is also not given.
yes, power input is not given means you have to consider 1. Just if it is given, consider it. If it is not given, just ignore it. Okay, this is how we have to go. Proceed. Okay, they have only given the slip factor. Now main motto is to find out the compressor efficiency. Now this is the formula for the compressor efficiency. T01 is given, RC is given. Now T02 is not given, right? If we know T02, then we can proceed.
Ma'am, T02 minus T01 is equal to psi mu u square upon Cp.
Okay, T02 minus T01 is equals
Psi
to
mu u square upon Cp.
psi is not there, mu u square.
U square by
Yeah.
Cp.
Cp, yeah, that is not there, right? So we can ignore it again by, right? How we got this? That's good. Work done means we know T02 minus T01, and which is also equals to mu u square, right? So from that relation we have got this fact. Now this value is given, mu value is given, u value is given, Cp is known. So Cp is 1005. Okay. Now T2 will become whatever the value you have, 0.92 into this value plus T1 is 294, right? You will get the T02. Substitute over here, you will get the efficiency. Now tell me, what is the U value? What is the U value you are getting?
451.
451.
Okay, 4
51.6.
okay, 451.6 meter per second. Now you apply over here 451.6. Now you see your requirement is T02 minus T01. So no need to find out separately. Okay, so your need is difference, right? So find out the difference alone. So you need to save time. Okay, you need to save time. No need to simply find out the parameters. So your change in T02 minus T01 will do it. Okay, so 0.92 into 4 into 451.6 square divided by 1005, and let me know what is the eta value.
Point 76.
Hmm?
0.76.
0.7662, right? That means 76.62 percentage, right? All of you getting the same answer? All are getting the same answer?
Yes, ma'am. 0.76.
Yes. Yeah. Okay, please ensure, again I'm telling repeatedly in the question, if they asked, find out 2 decimal place. Okay, decimal place. So in that they have not given in terms of percentage or something, 2 decimal place. So either it will, you have to write 7.7, right? 7.7. Do not give any space or before and after, and no need to write the anything. Okay, just type the answer virtually in the exam, right? Okay, next question. A centrifugal compressor has a deliver 35 kg of air per second. The impeller is 76 centimeter diameter, revolving at 11,500 rpm with an adiabatic efficiency of 80%. If the pressure ratio is 4.2:1, estimate the probable axial width of the impeller at the impeller tip if the radial velocity is 120 meter per second. The inlet condition are 1 bar and 47 degrees Celsius. From here, what is the main motto to find out? They just ask you to find the axial width. Okay, so remember the axial width formula which I have said before, that is A equals to pi d w. Okay, that means W you have to find, D is given, that is 76 centimeter, that is 0.76 meter, right? Now area is given. Okay, what else is given? They have given, this is the mass flow rate is given, mass flow rate is given, N is given, then adiabatic efficiency is given, pressure ratio is given, then see the weight of the impeller tip is a radial velocity has been given. Okay, that means CR value has been given at the tip. CR value at the tip has been given. How do you proceed? pressure given, temperature given. Tell me, how do you proceed? From here your main motive to find out this. Any idea? Mass flow rate is also given. What is mass flow rate? Rho A V. Now can I say rho into A, okay, of the impeller into CR? Can I write like that? Can I?
Yes.
Okay. CR is given. What about rho? How to find out the rho? Yes, very good. Already have shown you the formula. Rho equals to, what is the formula? P by R T. So we are finding. So one more thing, they asked to find for the tip. For the tip, that means we need to use rho naught 2. So we cannot use this one or neither this one. We have to use find P02 and T02. How we can find? They have given the efficiency again. They have given the pressure ratio. So pressure ratio means RC means P02 by P01. Okay, that is 4.2. P01 is given, right? P02 by P01 is 1 bar. So P02 is 4.2 bar. Can I say that? So P02 is, I got it. R is constant, is 4.2 into 10 power 5, 287 into T02. Now how I can find T02? Efficiency is given, eta C equals to T01 RC 0.286 minus 1. 286 I have written, gamma minus 1 by gamma, we will get 0.286. Okay, so directly I am writing that value by T02 minus T01. So here I know T01 RC is known, this is also known, so I can find T02. Applying that value over here, I will get my rho value. Substitute m dot value is known, 35, right? Rho value will be known, my pi into d in d is 0.76. Find out and tell me the answer. Okay, first tell me what is the value of T02. What is the value?
524.9.
522.
0.988.
Actually, I have not mentioned the value. Okay, let's see that. Okay, now substitute over here. You're getting 522.98. You will get the value of rho. So in
2.798.
two, sorry, 2.
0.7.
All of you getting the same answer?
Yes, ma'am.
Okay, that's great. Now 2.7, put, you got it over here, and find out the width of the impeller.
Ma'am, is it 0.043, ma'am?
0.043.
43, ma'am. Correct, ma'am?
I forgot to mention the answer over here actually. So let's check with others. So if it is getting, let me confirm that. Okay, others, just let me know what is the answer.
Ma'am, 0.043.
Okay, that's great. So this is the right answer, right? All are getting the same. Okay, correct. So you can understand that from a single parameter how they're asking the questions. Okay, same thing the gate will be doing. For small parameter you have to find out other parameters also. Okay, yes, now this is something different problem. Okay. A centrifugal compressor has a inlet eye 15 centimeter diameter. Now the impeller revolves at 20,000 rpm and the inlet air has an axial velocity of 107 meter per second. The inlet stagnation temperature 294 Kelvin and inlet pressure 1.03 kg per centimeter square. Determine the theoretical angle of plate at this point and the Mach number of the flow at the tip of the eye. Okay.
Is it density or pressure, ma'am?
It is in pressure. Okay, kg. So what is the unit for the pressure? Pressure is actually Newton per meter square. Okay, but here they have given kg per centimeter square. That means you have to multiply 9.81 to get Newton per centimeter square. Got the point? So you need to multiply 9.81, so you will get Newton per centimeter square. So that you need to convert again to Newton per meter square. Alright, inlet I is given. Okay, that is di is given, that is 0.15 centimeter. Then n is given. The inlet air has an axial velocity. Axial velocity means cr is given. Inlet cr1 is given. Then T01 is also given. This is also P01. Now blade angle at this point. So they have given the intake one. Okay, they have not mentioned whether the flow is whether their intake means either you have to consider the um, inlet guided vane is there or not there, whether it is with or without. Now first you need to identify whether it is with or without. Since they have not mentioned anything, so we will proceed with reason without inlet guided vane. Okay. Now what was the condition in the inlet guided vane? What was the condition? Do you remember? We consider that C suffix T
Theta is equal to 90 degree. Without, sorry, CT1 is equal to 0.
CT equal 1 equal to 0. Okay, the tangential velocity was 0, and when we are making 0 we got I think alpha 1 become 90 degree. Am I right? Alpha 1 become 90
Yes,
degree,
ma'am.
right? That means if alpha becomes 90 degree, sorry, becomes 90, CT becomes 0. Okay, this beta 2, this C,
Ma'am,
yes,
theta is 34.26 of ma'am.
30,
34.26 ma'am.
yes, yes. Okay, so we are considering this is u1, this is w1, this is cr1, right? So cr1 was given equal to c1. So if I take tan beta 1 equals to cr1 by u1. Now how to find u? U we can find pi dn by 60. We can find pi equal to d is 0.15 into again 20,000 divided by 60, whatever you will get. Then from there you are getting beta 1 value equals to 34.26 degree, right? What was the main aim? Was to find beta. So beta angle is known, blade angle is known. Now next is a Mach number of the flow at the tip of the eye. Now you need to find the Mach number. That means to in terms of Mach number. Okay, that means tip of the eye means what you need to find the relative that is V2 you need to find. Okay, you need to find the V2. Am I right? So once you know the V2, then M2 equals to V2 by A2. Okay, how you can find once you know V2? Root over gamma R T2. Okay, can you get it? So tell me, how do you find?
And the inlet pressure is 301.
Which one?
They always give the stagnation pressure. Inlet pressure now.
Sorry,
Inlet pressure, how we are taking stagnation.
inlet pressure. I'm not
Yes,
getting
ma'am.
your point.
How we are taking it as P01 instead of P1, I'm asking them. They are simply given the inlet pressure.
Yeah. It is they have given only P, right? So actually in ideal case the static and the stagnation will be considered same. Somewhere it will be writing P1 which is equivalent to P01 we'll be taking. So that's not a issues over here. So you can either of the thing you can choose, but not in the temperature. Not in the temperature. Okay.
Then we can use the relation, ma'am. P01 by P1 is equal to 1 plus gamma max 1 real square.
Yeah, you can use that. Now question, just see here the Mach number of the flow at the tip of the eye. That means when it is entering. Okay, the question, just read it very carefully. When it is entering into the eye, not leaving. Okay, this is a question they're asking when it is entering. That means they're asking what is okay, so what is V1 in terms of Mach number, W1 in terms of Mach number. Okay, just this is the at the tip of the eye when it is entering into the blade. Okay, this is what they are asked to find. Now first you need to find out what is a W1. Okay, that is a relative.
Okay,
What is a relative? How you can find? Again by using the triangle you will find the W1. Now after that gamma R is known, gamma and R is known. T1, how we will use T1? We will use this relation, already we have discussed. What was that? T01 minus T1 equals to velocity, that is CR1 square by 2CP. This is a formula. Okay, the axial velocity square by 2CP. Okay, now T01 is given, CR is given, CP is known. So from here you will know what is T1, that you will substitute over here, and that we will get the Mach number. Could you able to follow that? Could you able to follow? First of all,
yes, ma'am.
they ask the Mach number of the flow at the tip of the eye. Tip of the eye, that means when it is entering into the blade. Okay, now first you tell me what is the W1. How you can find W1? You know the angle. You can use either of the pattern, right? So you can use cos beta 1 equals to, maybe let's take u1 by W1. So W1 equals to u1 by cos beta 1. So you will get the W1 value from here. So this is the Mach number formula. Okay, W1 by A1. So root over gamma RT1. Okay, so use this relation. Gamma is 294 plus 107 square by 2 into 105, 1005. Solve this, you will get T1. Substitute that value over here. (1.4) into 287 into T1, you will get the value of Mach number.
Ma'am, is it 0.55?
Yes, absolutely. It's 0.558.56.
Yes,
Okay, 0.56. Okay. So tell me what is the value of relative velocity? What was the relative velocity you got? What was the value for the relative velocity?
190.
190. Okay, okay,
190, ma'am.
okay. And what was the T1 value you got?
288.3.
300.
300. Okay,
288.39.
okay, all right. So after substituting, you got this m1 equals to 0.56. Okay. Yes, this is a very simple problem, but let's try. Okay, the relative velocity of the air leaving a straight radial impeller of a centrifugal compressor is 100 meter per second. If the impeller tip speed is 200 meter per second for a slip-free operation, the absolute velocity need to find out at the impeller exit. Okay, so all the values they have given as a leaving, that means stage 2, that means near the stage 2 they have given. Okay. Note that question, it's a radial impeller. Okay, radial impeller means beta 2 is equal to 90 degree. So this is given as W2 value is given, U2 value is given. Now from there you need to find C2. Okay, now you solve by yourself and let me know the answer in round off to 1 decimal place. In 1 decimal place. Can you solve it, or should I help it? Students, can you able to find out the answer, or should I solve? Just let me know.
Ma'am, is it 223.6?
Yes, absolutely right. 23.6.
Yes.
Okay, and here the answer should range from 220 to 0 to 225.0. Okay, so let me give a recap that how to find out. So when that gave given the radial impeller, that means it should be something like that. Okay, that is, this is 90 degree, beta 2 should be 90 degree, and if the beta 2 is 90 degree, then CA2 will equals to CW2 or CR2 C2, and here will be U2 equals to CT2 or CW2, whatever it is. Now first I will find out this angle alpha 2, okay, using maybe tan alpha 2 equals to W2 by U. Okay, I will use this half, so alpha 2 I will be able to get the value. Okay, then again I will use some another one, cos alpha 2 equals to U by C2. Our requirement is to find the C2 value, so U by cos alpha 2, whatever I will get previously, and when I solve that we'll get around 223.6 approximately per second. Alright, okay, that was a very easy question. Okay, let's find for this one. Okay, a radial tipped blade impeller of a centrifugal blower has the following data: speed is given, outer diameter, inner diameter is given, impeller width at the entry is given, stage efficiency 70%, the absolute velocity component at the impeller entry is radial and has a magnitude of 22.67 meter per second. If the radial velocity remains constant through the impeller, determine the pressure developed at the power requirement. So assume the constant density at the air at 1.25 kg per meter cube.
Ma'am, stage efficiency means impeller efficiency.
Yes, not impeller, the compressor efficiency. Okay. Sometimes they don't use that particular component efficiency, they use the called as a stage efficiency. So n is given, then outer diameter is given, that is tip, inner is hub, width is given, efficiency is given. Now absolute velocity component, that is C entry, that is C1, is radial. Now what that mean?
Beta 1 is 90.
If beta 1 equals to, what is mean by the it is getting radial? It is means radial means when our tangential velocity becomes 0. Okay, when the tangential velocity remains 0, on that scenario we have to take that. If the radial velocity remains constant through the impeller, then what is the pressure developed and power and density is given. The main thing what you have to find is the pressure developed and power. Now what is the power? Let's start with the power. Power equals to mass flow rate into work done. Mass flow rate is, how to find mass flow rate? Mass flow rate we can find rho a v. Okay, rho a v. Now using this relation, again what will be the v? Rho a, this will be the equation to find out. Now rho v is given, a is known, that is how to find a equals to pi db. Okay, diameter is given, width is given at the entry, so you can find this one. CR1 is also given. CR1 is given. Otherwise you can find it out, CR1 to find out. Okay, so using that, how to find work done? Work done equals to u square, that you can find using this. Okay, right? So work done is known, this is known, you can find out the power. Now how to find the pressure developed? pressure developed, there is one more formula. Okay, here they have given efficiency. So eta C equals to, can I write in this way, that eta C equals to, that is Cp T02 prime minus T01 by Wc. Wc we know what is the value, eta C we know. Okay, now this can be also written as del H prime. So del H prime is also can be written as change in pressure with respect to rho. Del H prime can also be written as change in pressure by rho. So the pressure change can be found, rho is given. So using this relation you can able to find out. Okay, so please note this problem. Please note this problem for your homework. So you practice and let me know what is the value you are getting. The answer of the power is 7.02 kilowatt. Just ensure you are getting that value or not. And change in pressure is in 34.66 Newton per meter square. Just ensure this answer. Okay, are you getting this value or not? Okay, have you noted down the values given data?
Yes, ma'am.
Okay. So even as I've said in the morning class, that they will give you some kind of velocity triangle, and based on the velocity triangle they will ask you to find out the other parameters. Okay, so this kind of problems you can expect. This is a very simple problem, looks complicated but simple problem. What they have given here is, they have given the direction. This time theta represents the tangential, R represent the radial direction. That means this is the radial direction or the axial directions, and along this direction is a tangential direction. So they have given u value, we have given CR1 equals to CR2. Okay, so from here to here the value is given 40. That means I can take up the remaining value. That means from here to here is 60. 100 minus 40, I will get the remaining this value. Now again, using the triangular forms and all those things, I will able to, this value is given as 30, this value is given as 30. So using this triangle I will able to find out the unknown parameter, the specific work output. So specific work output is nothing but that CW2 into U2 minus CW1 into U1. Okay, so using this triangular diagram, triangle, I will able to find out the CW2 U2. Okay, so here U1 is equal to U2, right? So I will able to find CW1 using this triangle, because the angle is given, this is known, this value is known to me, right? This value is known, I know the angle, I can able to find out this much parameters, able to find this much parameters. Okay, so I will substitute, I will get my answer. Okay, so specific work output means whenever we get in terms of kg with respect to unit kg, then only we call as a work output. That is the difference between work output and work input and with a specific work output. Okay, when there is something with divided by kg with unit mass, it becomes a specific, and specific work output is an which kind of property, can you tell me? It's an extensive or intensive property? Which kind of property it will be? It will be intensive or extensive property? Intensive property. It is independent of mass. Okay, it will be a property, intensive property. Very good.
Ma'am, the CW2 is equal to C2 now in this? CW2 is equal to C2 and
CW,
C2
which one?
Ma'am, let CW2 value in work done.
CW2 equals to, sorry,
C2.
no, here they have given the triangle, right? So you need to find CW2 will become this one. CW2 will become 60.
Acha.
Using this triangle you have to take, right? It will form a triangle. Got it? Okay. So that's all the problem. Lot many problems are there. So yes, we will just talk about the pre-wheel and the importance of that. Okay. So why then there is a concept called a pre-wheel in a centrifugal compressor. Okay, that is that it is a special type of motion provided to the air at an entry of the centrifugal compressor. Now what is the benefit of this pre-wheel? It avoids the shock wave formation. Okay, so what it happens, we use an inlet guided vane. Okay, so that it helps to create a kind of smooth entry into the centrifugal compressor, and the another reason, it avoids the shock wave formation, and if the shock wave formation can be reduced, the losses will also be reduced. But there are some disadvantages in this pre-wheel consideration. It reduces the work output. Okay, because pre-wheel decreases the oiler's work. Okay, pre-wheel decreases the oiler's work because there will be some reduction in overall pressure ratio. There will be reduction in the overall pressure ratio. So if the pressure ratio is that is RC is decreased, overall pressure ratio is decreased, then the efficiency will also decrease because they are directly proportional. Okay, this is a small concept but huge point in it. Okay, then coming to next phase is losses of centrifugal compressors. Okay, so there are of basically two different losses. Okay, one is the one losses can be occur due to incident loss. Okay, another one due to a frictional loss. Okay, so next, now frictional loss, you can say that it is proportional to the square of the absolute velocity and the mass flow rate. These terms are very important. Okay, how they are interconnected with each other. So if the absolute velocity is more, then again the pressure losses will be more. If the again send the just give me a second. The mass flow rate, okay, they are directly connected with the mass flow rate. Okay, so that means if the mass increase in mass flow rate, as well as there will be increase in pressure loss. Next one, this incident loss represents that it is proportional to the drag coefficient. Okay, so it incident losses occurs based on the component thickness, the blade size, the number of blades, and all those parameters. All those parameters. Okay, so this is directly connected with the drag coefficient. Again, this is also same thing, as we increase in mass flow rate, this is also dependent. This is also dependent with the mass flow rate. As we increase the mass flow rate, you can see initially the loss gradually decreases at some point. Again after that, again by increase in mass flow rate, again the incident loss increases. Okay, So there is some limit where the incident loss can be negotiable, can be considered as an effective one, but beyond that, further increase of mass flow rate, it will lead to an again increase in incident losses. Okay. Now next, another very important topic. So yeah, so choking and surging. Okay, this is another important topic, and you need to understand this concept. So before surging and choking, you must need to understand how effectively we need to design this centrifugal compressor. Okay, now to increase the overall efficiency of the engine, now every component must be efficient, then only the overall efficiency will be improved. Now what it does in the centrifugal compressor, we have the inlet, the air enters from there, then they will have the blades, right? We have the blades over there. Now from the blades the swelling movement takes place, the air moves to the diffuser and expels out. Now that diffuser, when the air enters to the diffuser, and from the diffuser where it will go to the combustion chamber. It will, because from the entire jet engine, after this compressor, it has to move to the combustion chamber. So how effective the pressure ratio will be, the pressure will be compressed, better will be the combustion, the mixing of air is possible. Okay, so all are directly connected. Now one important fact that you need to know, when the air moves, okay, the diffuser outlet velocity, okay, the diffuser outlet velocity should range from 80 to 95 approximately meter per second. It should not increase beyond that. It should not increase beyond the 80 to 90. Okay, now why? These are the part of the compressible effect. So we have to avoid, there should not be any kind of adverse pressure gradient over the blades, even at the when it is moving out from the diffuser to the combustion chamber. Okay, so we have to see, because as the static pressure increases, then definitely the velocity has to be less. Now we have to decelerate the velocity, and the velocity should be ranging within to 80 to 95 meter per second. Okay, in ideal case they consider 90 meter per second. So this can be another kind of questions. Okay, so these points are very important. Now what happens if this is a blade, okay, it is leaving out or expelling out from the these flows are expelling out from the diffuser, right? It should not have any sort of reverse flow direction, because reverse flow, this is an important thing. Yes, please.
80 to 95 meter per
80 to 95 meter per second, and in standard case they consider to be as 90.
Is it? I didn't get what type of velocity is that.
It is a diffuser outlet velocity.
Okay.
Diffuser outlet velocity, because when this velocity is moving, where it is moving to the combustion chamber, it's moving to the combustion chamber. Okay, now if there is a forming of AD, because if I increase the speed, right here, if I am increasing speed to more than 100 and beyond that, what will happen to this blade? Okay, or in the zone, it will start to cause a pressure gradient because of reverse flow, or I can say it will lead to AD formation or turbulency, right? So what they do is, the diffuser, the passage, okay, the passage from the compressor, and when it is entered to the combustion chamber, right, there will be some passage, something like that. The angle subtended to that passage should not be more than 12 degree, 11 to 12 degree. That is another a part of concept, because using that divergence, they can ask why they use a divergence section, because to avoid the AD formation, to avoid AD formation, or I can say if the AD formation avoid means, or to avoid adverse pressure gradient, okay, or avoid to form stall, or I can say, or to avoid turbulency, okay, or I can say avoid reverse flow. So all the basic idea is this. I need to, or I can say the boundary layer separation, or I can say the boundary layer separation, right? Clear? Now there is one more thing. So okay, this is clear, right? Just let me know if this is clear or not. Just let me know if it is clear.
A little confusing for me.
Yeah, what is the confusion? Just let me know.
This is regarding surging or choking, ma'am. Or
No, this is not surging and choking. I have not came up with this topic. Before coming to that topic, I am just explaining what is happening if this happens. I have not came up with the surging and choking concept. Okay, I have
to be
not.
frank, I didn't understand. Sorry, ma'am.
Okay, no issues. Okay, see, all right. I think what we can do is, I think it is a huge thing altogether, right? It's a small topic.
Yeah,
Maybe we can take up in the next, or I will put it in my notes. Okay,
yeah,
right? So the main thing is everything is collapsed and altogether you're putting inside your brain. That is the main thing,
yes,
right? Am I right? Okay,
Yes,
okay.
yes,
ma'am.
ma'am.
All right, all right. It's a small, very small topic. The detailed notes I'll be providing to you. Maybe by today evening I will be putting up that notes. You can access, and the video will also be uploaded. Okay. All right.
Okay.
All right.